Now, electric and magnetic fields are vector fields. That means you can't just say the field is 3 volts per meter at a particular place. It's not just a number, it's got a direction. So how do we describe those? Well, one way you can plot these things is with lots of arrow diagrams. Here's an example. So what have we got here? Looks like we've got a positive charge here because the electric field is pointing away from it. The arrows with their bases nearby are very long ones, which means the electric field is very strong at these points. And as you go further away, the arrows get smaller, which is a normal Coulomb law type approach. Over here, it looks like we've got a negative charge. The arrows point inwards, and the ones very close have enormous distances, the ones further out are smaller. So that's one way of doing it. You just do a huge grid of arrows. Now, of course, this is showing us what the field is here and here, but halfway in between there's a field as well. And of course the real field is three-dimensional, so you've got to imagine a huge bunch of arrows floating in space, which is rather hard to plot. Another approach which is sometimes used is streamlines. What you do here is you take all the arrows here and then join them up. So it would have been a strong force here, and then the vector goes all the way around like that. In this case, you can't use the length of the lines to show you how strong the field is. The field is strong where the lines are bunched close together. So A's probably got the strongest field here, whereas over here, where the lines are quite a way apart, the field is relatively weak. How do we describe vectors mathematically? Well, we typically write a vector by putting an arrow over the symbol. So if you see an arrow over something, that's telling you it's a vector, so it's got a direction. And if we want to write down exactly what's going on, we could describe it as, let's say, an arrow pointing 30 degrees upwards of length 10. That's one way to describe it. An easier way is components. So we might say the electric vector E is going to have 3 components, an x, a y, and a z component. So we need axes. In this course, we'll typically use x this way, y that way, and z that way out of the screen towards you. And so our components will be E x, E y, and E z. So if, for example, we had a vector like this, that would be Ex, which would be large and positive. Ey would be this, positive but a bit smaller, and Ez would be 0. Whereas if we had a vector that looked something like that, now Ex is that length there, which is going to be small and positive. Ey is going to be 0, and Ez is going to be large and positive. The length of a vector, so the distance, say, from here to here for the green vector, or from there to there for the purple vector, is normally written as follows. It's called the modulus of a vector. And you do the vector and then put big vertical lines on either side. So that tells you how long a vector is. It's often what we call like the strength of a vector, just ignoring the direction. And you can work that using Pythagoras' theorem. That's going to be the square root of each of the components squared added together.